Hi, and welcome to yet another presentation on thermodynamics. Today we will study about second law of thermodynamics. Let's see what is an engine. We can study second law of thermodynamics if we understand engines well. So let's understand what is an engine. Engine or heat engine is a device which converts heat to mechanical work. The engines that you see all around yourself take air, they take fuel, burn the fuel, which generates heat, and that heat is converted to mechanical work. Now, Carnot was one person who got interested in the efficiency of heat engines. During his days, heat engines worked by steam, that is, they used steam to work. What he found that no engine can completely convert all the heat that is given to it to work. Heat was always rejected. Now, in modern day engines too, whenever fuel is burnt, the heat is converted to mechanical work, but heat is rejected by the engine from the radiator, and heat is also rejected by the engine from the exhaust. The exhaust is always hot. So, Carnot's devise an engine, or Carnot devised an engine. His engine would take heat reversibly at a high temperature and also do work reversibly. It was an ideal engine that would convert the maximum amount of heat to work. All engines, all practical engines would have an efficiency lesser than the Carnot's engine. So here's the Carnot cycle, that is the cycle of the engine itself. In a Carnot engine, the engine would take heat QH at temperature TH. The heat would be taken reversibly, so the heat would be taken by the engine isothermally. After isothermally taking the heat from this point to this point, the heat would be converted to work adiabatically from this point to this point, and that too in a reversible process. After which heat QC would be rejected to the atmosphere at temperature TC. This is followed by adiabatically compressing the fluid once again and bringing it to a temperature TH. Therefore, for the Carnot cycle, what Carnot found was that QC by QH, the ratio of heat rejected to heat given, was equal to the Kelvin temperature TC over TH, where TC is the temperature at which heat is rejected and TH is the temperature at which the heat is given to the engine. For a reversible cycle, QC by TC is equal to QH by TH, or we get QH by TH minus QC by TC is equal to 0. We can say for a reversible cycle now that the summation of all the heat, that is dQ by T, is equal to 0. Now this naturally arises from the last equation that we have written. Or if we define dQ by T as S entropy, where entropy is defined as dQ by T, for a cyclic process, the entropy change is equal to 0. For any cyclic process, delta S is equal to 0. Therefore, we can say that entropy is a state variable. Now, why do we propose this, that entropy is a state variable? Now, for the reversible cycle, we saw that if we start from a point and come back to the same point, the change in entropy is 0. Now, what if we perform a irreversible cycle? Okay, all irreversible cycles can always be approximated by a set of reversible processes, which would be a reversible cycle. Okay. Now, for a reversible cycle, the change in entropy is zero. Therefore, we can conclude that for an irreversible cycle also, the change in entropy is zero, because the irreversible cycle can be approximated by a reversible cycle. So therefore, change in entropy for an irreversible cycle is also at zero. By this, we say that entropy is a state variable. Why? Because we start from a point, perform a reversible or an irreversible cycle, come back to the same point, and if we measure the change in entropy for the entire cycle, whether it is reversible or it's an irreversible cycle, we find that the entropy change is zero. Therefore, entropy is a state variable. Entropy depends on the state at which the fluid is present. Now, entropy can be further understood with a thought experiment or a box inquiry, as we call it. Now, what does this box contain? First of all, this box is a perfect isolation box. No heat can escape from it. It has two masses, A and B, and those masses are equal. Mass A has a temperature Ta and mass B has a temperature Tb. Now, Ta is greater than Tb. What we do is we bring the blocks together. Now, heat naturally will transfer from block A to block B. The change in entropy of block A is going to be minus dq by Ta, which is going to be equal to minus m, that is the mass of the block A, into C, the specific heat, Ta minus Tb, the temperature gradient for heat transfer, divided by Ta, that is the temperature of the block. The change in entropy of B is going to be minus dq by B, which is going to be plus mc Ta minus Tb upon Tb. Now, if we add the entropies, that is dSA plus dSB, we get the result mc Ta minus Tb the whole square over Ta into Tb. Now, change in entropy of the universe is equal to change in entropy of the system plus the change in entropy of the surroundings. Now, change in entropy of the system is dSA plus dSB, and change in entropy of the surrounding is zero. That is because no heat has been transferred to the surrounding. So we get the change in entropy of universe as mc Ta minus Tb the whole square TATB. Now, till Ta is greater than Tb, look at the previous equation. Till Ta is greater than Tb, ds universe is going to be greater than 0. If Ta is equal to Tb, ds universe is going to be equal to 0. What this means is, till block A transfers heat to block B, the change in entropy is always going to be positive of the universe. Okay, the moment the temperature of block A and block B get equal, the change in entropy is going to be 0. It means when we start the process, the entropy of the universe is continuously going to increase. But the moment the temperatures of the blocks become equal, the change in entropy of the universe is going to be 0, or the entropy is going to reach a maximum. From this, we also get a conclusion that for all spontaneous processes, change in entropy of the universe is always positive, or ds universe is greater than 0. Now, here a clarification. What exactly is a spontaneous process? Take a matchstick and strike it. It immediately burns. And the burning goes on. You need not give any work. for the burning to continue. Take a ball, keep it at a higher elevation, give it a slight push. It falls. If you kept it on a slide, it would roll down. To make it roll down, you don't have to give it any work. It's a spontaneous process. It will happen by itself. So these are spontaneous processes. Now take a body which has higher temperature and a body which has lower temperature. The moment you join them, heat will transfer from a body of high temperature to a body of low temperature. It won't happen vice versa. Heat spontaneously transfers itself from the body of higher temperature to the body of low temperature. It doesn't require any work to transfer the heat. So these are spontaneous processes. And for spontaneous process, ds universe as shown is always greater than 0. But when equilibrium is reached, the ds universe is 0. Taking the three thought ideas or experiments that I had put out now, if the ball, which has been put at a higher elevation on a slide, slides down and reaches the ground, after that it's going to just stay on the ground. Okay, it's not going to change. It has reached its equilibrium position, right? If I take two bodies, one which is hot and one which is cold, and join them, heat transfer will happen from the hot body to the cold body till the temperatures are equal. That's equilibrium. After that, no more heat transfer or net heat transfer will happen from one body to another body. Now let's lastly take the striking of a match. You strike it, the burning occurs. The burning occurs, it consumes all the fuel and all the wood of the match. After that, it extinguishes. All the heat is given away and it reaches the room temperature. That's the equilibrium. After that, it's no longer going to heat up and give any heat. It stays there at till time infinity. So that's an equilibrium state. So at equilibrium state, the change in entropy of any body is 0. Now we know, we looked at the Carnot engine and we declared it for an irreversible engine also, that for a reversible engine, okay, or for an irreversible engine or a process, the change in entropy is 0. Now here we introduce a new concept, that of a reversible process. Now for a reversible process also, if we take the change in entropy of the process and change in entropy of the surrounding and we add it up, that would be the change in entropy of the universe. For a reversible process, okay, the change in entropy of the universe is 0. It means that the change in entropy of the process and the change in entropy of the surrounding are equal to each other but opposite in sign. Okay, for an irreversible process, the change in entropy is always greater than 0. We will see this in an example. We will definitely see an example at the end to understand this. Now let's take the steady flow entropy equation or study the steady flow entropy equation for an open system. The area in blue is my open system. Okay. Now a flow M in goes into it and a flow M out comes out of it. Heat Q is given to it. There is a shaft which goes into this system, and at the end of the shaft we have an impeller. So when we rotate the shaft, the fluid is being churned. Now the change in entropy per unit time of my system. Okay, system is the blue area. The change in entropy of the system is going to be equal to, let's take it from the rightmost end, Sgen. First, the churning of the fluid causes irreversibility in the fluid. So therefore it increases its entropy. Okay, because churning is a friction process. Friction always produces heat. So churning is going to cause an entropy increase in the fluid. So ds by dt, that is change in entropy of my system, is going to be equal to Sgen plus heat given per unit time divided by the temperature at which it is received by the temperature. Please note down the T here is the temperature at which the heat is received by the system. Now, heat transfer is always going to take place across the boundary of the system. Now, when heat is given here, what is going to be the temperature at the boundary? That is the temperature we are going to put here. Okay, so the change in entropy of the system is also equal to the summation of all the heats given and taken divided by the temperatures at which either they are given across the system boundary or taken from the system boundary, right? And also it's going to be the summation of all the mass flows going in and out multiplied by their specific entropies. So this is your steady flow entropy equation for an open system. Now, let's apply it to a closed system. In a closed system, no mass can flow in, no mass can flow out. So therefore, the first term in the RHS is going to be 0. Now, what if it is a reversible process? If it's a reversible process, then S generated is going to be now 0. So change in entropy per unit time of a closed system undergoing a reversible process is going to be equal to nothing but summation of Q dot by T. Now, if we apply this to a Carnot cycle, the change in entropy per unit time is going to be nothing but plus summation of QH by TH plus minus QC by TC. We took minus sign for QC because it is the heat which is being rejected. Now, for a steady state always, ds by dt is 0. Okay. What is a steady state? A steady state is a state where the quantity is not being accumulated. Now, in a Carnot's engine, entropy is not getting accumulated. Whatever heat is coming in, it's being converted to work, and the rest of the heat is being rejected off. At no point the heat is getting accumulated in the Carnot's engine. Therefore, there's no entropy generation in the Carnot's engine. And therefore, ds by dt, that is the LHS, is going to be 0. And therefore, we get for a Carnot's engine, QH by TH minus QC by TC is equal to 0. Now, this equation which I have written can be applied to closed systems also. And with its application to a closed system, to a Carnot cycle, I have proved that this equation is right in its ideas. Now, let's take a problem to understand how reversible process entropy changes are 0 and how irreversible process entropy changes of universe are greater than 0. So let's take a problem now. Now in this problem, a 5 kg copper ball at 75 degrees Celsius is dropped into a 12 kg water, which is initially at 5 degrees Celsius, and all this is done in a well insulated container. So whenever we use the words well insulated container, it means it's an isolated system. The entire process now, that is the dropping of 5 kg copper ball into 12 kg water, is a process which is happening in isolated system, right? For an isolated system, heat and mass cannot travel across the boundaries. Now, the first thing that is being asked is, what is the common temperature? Now, if we apply first law to the isolated system, the change in internal energy of the isolated system is going to be equal to Q plus W. Now, Q and W for the isolated system, it is zero because no heat can transfer across the bodies of the isolated system and no work can also transfer. And it's a closed system because no mass can also transfer, and I've applied the first law of the closed system. So delta U is going to be equal to zero, which means that change in internal energy of the copper ball plus change in internal energy of the water, this is going to be equal to zero. From this, we get 5 into zero point 0.5 into Tf, which is the final temperature of the copper ball, minus 75 plus 12 into 4.2 into Tf minus 5 equal to 0, wherefrom we get Tf as 8.308 degrees Celsius. Now, when a body is being heated or cooled, how do we calculate its entropy change? Well, this is given in the square yellow area. I have put the derivation. The change in entropy of any body is dq over T. Now, change in specific entropy is going to be C, that is the specific heat, P, or this is at constant pressure, but neglect P for now. This is going to be C into dt, right? Over T. Now, the change in specific entropy, for the change, total change from 0 to S, we integrate it off. Now, the entropy is 0 at temperature Tref. So we take some reference temperature where we fix the entropy of the body as 0. Now, in this particular problem, we can take the reference temperature as 273.15 plus 25 degrees Celsius. Okay, that would be roughly 298. Okay, Kelvin. Now, here, after we integrate it, we are going to get the change in specific entropy as Cp into ln T by Tref. Or the total entropy change is going to be nothing but the product of the mass and the specific entropy change. Now, change in entropy of copper is going to be 5 into zero point 0.5 into final temperature over the initial temperature by applying this formula. If we apply it from state 1 to state 2, state 1 was for the 5 kg copper ball, it was at 75 degrees Celsius. Now, state 2 was 8.308. Now, that is the integration we have done, and we have got this equation. So, therefore, change in copper entropy is this, which is minus 5.5316. Change in entropy of water calculated similarly, which is 0.5958. And when we add the change in entropy of copper to that of water, we get 0.6423. Now, this was a spontaneous heat transfer. We did not have to do any work to transfer heat from the copper body to water. Therefore, it is quite natural to get delta S universe as a positive quantity or greater than 0, and we have got it here. Now, delta S universe is going to be delta S system, which is that of copper and water, and delta S surrounding, which is 0. And what we do is when we add it, we get the value as 0.06423. Therefore, the entropy has increased because this was an irreversible process. So, hope you have understood the concept of entropy, at least the basic idea of the concept of entropy. Do subscribe my channel for very interesting lectures on thermodynamics, and do put your comments. If you have any queries, put it in the comment section. Have a great day. Bye.